Okay, we're going to continue with chapter 4, and the first thing we're going to look at in the second part of the lecture is something called the photoelectric effect. Now, the photoelectric effect is an effect that's seen in metals, where if you shine a light on a metal, you can actually get electrons to flow in that metal as a current. Now, there are some weird things about this photoelectric effect. The first thing is that there is a minimum frequency. Now, it doesn't matter how bright the light is. If the light is not of a particular frequency, no electrons are going to flow in that metal. So that's kind of weird, right? Because imagine you have red light shining on this metal. You can see in the picture here, we've got infrared light, we've got red light, and we're not getting any electrons being emitted or flowing through this metal. And it wouldn't matter how bright that red light would be, you're not going to get any electrons flowing. Now, on the other hand, once you start getting the blue light and then the ultraviolet light, then you start getting electrons flowing, you get currents. Now, what happens if you take these guys and you turn up the intensity? Well, when you have increased intensity, you get more electrons, but they all have the same energy. So the electrons emitted from this blue light here, they would all be low-speed electrons because they have the energy associated with the blue light. And here's the ultraviolet light. Here, regardless of whether it's dim or bright, you're going to get very high-speed electrons. If you make it brighter, you just get more electrons flowing, but they're not going any faster. They don't have any more energy. Now, the fact that the photoelectric effect behaves this way actually cannot be explained if light is just a wave phenomenon. It can only be explained if light behaves like a particle. And this was the experiment that made Albert Einstein reconsider a century's worth of physics. For over 100 years, there was evidence upon evidence piling up that light was a wave and just a wave. But then there started to be these experiments like this one that actually started to show that light could also behave like a particle. It would do things that could not be explained if light was just a wave. And so Einstein's the one that came up with the idea that light could also behave not just as waves, but also something that has particle-like characteristics too. Now, we can understand this because each color of light has a particular frequency, and that frequency is related to the energy. Think about like if we make light the old-fashioned way of shaking a charge back and forth, the faster you shake the charge back and forth, the higher frequency of light it'll emit, but it's going to be moving faster, so it has higher kinetic energy too. So the energy that is emitted in a particular beam of light is going to depend on the frequency of the light or the frequency of those little light particles that we call photons. And the equation that we can use is this equation here. The energy is equal to this constant value h, which is called Planck's constant, times the frequency. So this F stands for frequency, and the E stands for energy, and this H value here is this constant Planck's constant. And you can see it's 6.63 times 10 to the minus 34. So it's a very, very, very small value. But that is the relationship between the energy and the frequency in a beam of light, or in a photon of light, actually. Now, here is a slide showing what we were talking about previously about the way that electrons can jump up into higher energy levels and then fall down. And so here we see a case of an electron. It's gained some energy from a photon, UV photon of UV light, and it jumps up to a higher energy level, and then it falls back down home, and it gives back that energy as a UV photon. Now, here is a different scenario where a higher energy UV photon comes in, And that guy doesn't just jump up one level, but it jumps up 2 levels. Once it's at 2 levels, it has two possibilities to decay. It can go straight home, in which case it gives back all the energy as another UV photon, or it can skip. And so on this skip, it might give off a visible light photon, and on that skip, it might give off a UV photon. But you can see that there is a discrete number of possibilities, and that corresponds to a discrete number of lines in its spectrum. Now, we've also talked about absorption spectrums, and the absorption spectrum occurs when the light passes through a gas and gets absorbed. Now, remember, it only absorbs the colors of light that gas would give off if the gas were emitting light, because those are the energy levels that correspond to those electron jumps. And so that's how those gases absorb the energy. The energy is just the right color to create those electron jumps, and so the electron jumps up and it absorbs that energy. Now, we've looked at atoms that have just one electron, hydrogen. If you have multi-electron atoms, that is atoms with more than one electron, there's lots more shells and lots more opportunities for different electrons to jump from one place to another. And so that gives us much more complicated spectra, that is spectra with a lot more colors in it. And the other thing that's maybe worth noting is that if you ionize an atom, that is, you rip off some of the electrons or you add some electrons to it, it can actually change the gaps between the different energy levels, and that will change the spectra that those atoms give off. So an ionized atom will give off a slightly different spectrum than an unionized atom. And as we said, the whole purpose of this is that these spectra can be used to identify atoms or molecules like a fingerprint. And so if you're looking at a spectrum, you can say, oh, these colors correspond to helium, and these to neon, and these to helium, and this one's oxygen, and this one's hydrogen. And so you can figure out you've got light being emitted by this guy here. You can figure out what it's made out of by the fingerprints of the different colors it's giving off. Those fingerprints correspond to specific chemicals. And this is really the heart of what spectroscopy is. The title of our chapter is Spectroscopy. It's all about identifying things from the light that they give off. Now, what about when you have molecules? Remember, a molecule is two or more elements bound together by a chemical bond. And so here we have the example of carbon monoxide. It's a single carbon atom and a single oxygen atom, and they're bound together by sharing an electron. So they each share this electron here, and this kind of bond where our two atoms share an electron is called a covalent bond. You might have learned that in chemistry at some point. You don't really need to know it for astronomy, but just if you've ever heard of that, you might remember that. But anyway, here's the thing. So when you have a molecule, you've got lots more shells that electrons can jump around, and you have an initial structure because that chemical bond holds the carbon and the oxygen together like a spring. And just like something on a spring, these guys can vibrate back and forth. And what do vibrating charges create? Electromagnetic radiation. Now, here's the thing. If you've just got a gas of isolated carbon monoxide atoms, it turns out, just like the electronic transitions, the rates of vibration for these molecules are bound to certain discrete values. That means there's only certain colors that it can vibrate at, certain frequencies that it can vibrate at. And so it will be able to absorb those frequencies, and it'll be able to emit those frequencies. But it does because of this vibration. Now, the other thing that can happen is that this guy can rotate, it can spin. But the thing that is tricky is, again, these rotation rates correspond to specific energies. There are only certain frequencies at which it can spin. And if it encounters those frequencies of electromagnetic radiation, they'll start to spin and absorb it. Or if they're already spinning in it, they can give that off. And so these are the ways that you can get light. You can get the electronic transitions, the electrons jumping around like we talked about. There's vibrational transitions, and there are rotational transitions. And over here on the left, you can see some different facts about these different kinds of transitions. I'm not going to read them out loud to you. You can read. But these are important data that describe features of these different types of transitions. Now, just FYI, the way that your microwave oven in your house works is that it emits radio waves in the region of the spectrum called the microwave region of the spectrum. But really, it's just sending out radio waves. But it's sending out radio waves at the frequency to make water, which is H2O, to make water rotate. And so what happens is those radio waves penetrate the food, and any water molecules in that food will start spinning. And then remember, as things move faster and faster, that's generating heat. It's generating higher temperatures. And so that's how the food is cooked in the microwave. It's basically turning your food into something that's absorbing the electromagnetic radiation, and that's how it heats up, because the water molecules are spinning. You might have noticed if you put like a really stale roll in a microwave and you heat it up, it actually comes out not just warm, but kind of moist. And that's because those water molecules have been excited and spun around a bunch. And it's a very different way of cooking, like from a conventional oven, which just simply has a high temperature element sending out radiant heat. So the normal oven cooks the food from the outside in. The microwave actually cooks it from the inside out, which is a different approach. Now here we see the spectrum of hydrogen, which we've already looked at. But when we looked at it previously, we were looking at the spectrum of individual hydrogen atoms. Hydrogen normally forms a compound called H2, that is, two hydrogen atoms bound together. And if it forms into the hydrogen molecule H2, we call that molecular hydrogen. But if we just have individual hydrogen atoms, we call that atomic hydrogen. And you can see the two different spectrum. With atomic hydrogen, you just get just a few lines. With molecular hydrogen, you see lots and lots and lots of lines, because with molecular hydrogen, again, there's lots more different opportunities of jumping around energy levels, and we have the other methods of generating spectral lines, the rotational transitions and the vibrational transitions, so it makes for a much richer spectrum when you have a molecule as opposed to individual atoms. So just recapping some of the things that we've talked about, things that you can determine from the light coming from a distant star. We can get the chemical composition, that's what the star is made out of, by looking at its fingerprint spectrum. We can find its temperature using Wien's law. We can actually find its radial velocity. That's how fast it's spinning. If a star is spinning, we can see how that happens, and I'll show you that in a minute. Another thing that we can find, it should probably be just the regular velocity. How fast the star is moving away. We can use the Doppler effect to find that. And not just how fast it's going, but also which way it's going. If it's coming towards us, it'll look more blue. If it's going away from us, it'll look more red. So, and how much more red or how much more blue tells you how fast it's going. So just by looking at the different colors and intensities of light coming from different stars, we can tell a lot about them. And here I've included a chart from your textbook which sort of summarizes all these different things that we can tell and how we can tell them. Now, I mentioned in one of the previous slides that we can actually tell if a star is spinning, we can tell how fast it's spinning and what way it's spinning by using that Doppler shift again. Now imagine you're right here and there's a star over here and it's spinning around like that. So if I have that, then the part of the star this way is going towards you, and so the light from this side of the star will look a little bit more blue than the light coming from the center. And here, that star is rotating in the other way, so it's going away from you. So the light coming from this side of the star will look more red than the light from the center. And that actually makes the spectral line broaden or sort of get fatter. And it also lets you see how fast it's spinning based on how much broadening you get, how much more this side looks blue and this side looks red. And so that is a process by which we can actually tell if a star is rotating and how fast it's rotating, which is kind of cool. And so this slide is kind of showing how that broadening works. And so if the star were standing still, a particular line that it would be emitting might be this line right here in the middle. But here, the part of the star spinning is coming towards you, so it looks more blue, and so that line gets shifted to the blue. Now, right here in the middle, it's still being shifted to the blue, but it's not going straight towards you. It's kind of coming at an angle, so it's shifted to the blue, but not as much. Over here, on this side of the star, you get the red shifting. And so what you actually see is a combination of the red and the blue, and so when you look at the actual line, it looks fatter. And so we call that the broadening of the line. And based on how fat it gets, how much broadening there is, that will tell you how fast it's spinning, and you can do that calculation. It's again, just a really neat thing that we can tell all this stuff just from looking and understanding the light that's coming from these stars.